Okay, and we're using this to look at an example of sort of brute force enumeration in the service of approximation algorithms. We're using the same technique that we used with knapsack, which was that we actually are going to guess the value of the optimum in a sense, or guess, I shouldn't say the value of the optimum. We will guess some target completion time t. And we are then going to try to design a schedule that finishes within t. And if we can do this, then we obviously have a route towards finding an optimal t, right? If we are able to sort of, given a t, find a schedule that completes in time t if one exists, how can we use that to optimize our completion time? Yeah?
Binary search.
Binary search, right? So then we'll binary search for the right t. Right? Obviously, if we set t too low, we won't be able to find a solution. If we set t too high, we will. So we'll be able to use that to decide whether to move t up or down in our binary search. And so last time we started by looking at this sort of special case of k distinct job sizes. Right? And we looked at a sort of brute force, a dynamic programming enumeration for solving this, where we define a machine type, which just specifies the number of jobs of each size. And so there were n to the k machine types, right? And we could similarly define an input instance to be the number of jobs of each type, or each size, that we want to schedule. And so there are n to the k different input instances as well, right? Now we're going to limit ourselves to the feasible machine types, which are the ones that complete in time t. Okay. So whatever the optimal schedule is, assuming, if t is the optimum value for the problem, then each of the machines that's running is a machine of one of the feasible types. Right? So deciding whether we can schedule a certain input instance in time t is just asking whether there is a collection of machines of feasible types that together can take all of the jobs in the input instance, right? And so we discussed last time how we can create a dynamic program, right? Given instances solvable by m-1 machines, we can find the instances by m machines, right? All we do is we take each of the instances that's solvable by m-1 machines, and we try adding each feasible machine type. And this gives us a new set of jobs that we can solve in time t using m machines. So if we do this for all of the m-1 machine solutions, then we end up with all of the m machine solutions. In other words, we find all of the instances that can be solved in time t using m machines. So is that clear? That's where we sort of left off last lecture. I want to pick up from there. Okay. No questions about that? OK. So what do we have to do in order to get an actual approximation algorithm? Well, we have to deal with this random assumption that there are only k distinct types of machines, right? So how are we going to get around that? What I'm going to do is I'm going to combine the sort of enumeration technique that I just described with the rounding technique that we demonstrated just before the enumeration. So if you remember, I gave you a solution that was able to, that basically relied on the fact that if you schedule the k largest jobs optimally, then, right, so scheduling the k largest jobs, then you get an algorithmic solution whose value is at most the optimum plus the k plus first largest job, right? If you schedule the k largest jobs optimally, then you schedule everything else. And the argument was that, you know, if one of these later jobs defined the completion, then because it was added to the smallest machine at the time, it can only add pk plus 1 over the true optimum solution. Okay, and so that was another piece of what we did last time. So we're going to combine those two ideas. So in particular, I'm going to, again, I'm going to continue to have this sort of guess of the optimum time t. Right? And now I'm going to divide my jobs into two classes. Okay. So if my pj is bigger than some epsilon times that time t, I'm going to call that a large job. And if pj is smaller, then that's going to be a small job. Okay. And I'm going to think about the large jobs and the small jobs differently. Okay. Now, actually, the small jobs are easier to think about, so let's do that first. If I've somehow managed to take care of large jobs in some kind of optimal fashion or near optimal fashion, what should I do with the small jobs in order to get a good schedule? Or what can I do with the small jobs in order to get a good schedule? Yeah?
Can you use the greedy?
Exactly. So for the small jobs, greedy works. Right? I'll just use Graham's rule. I'll take whatever solution I had for the large jobs, and I'll just pile the small jobs onto the large jobs. Okay? Why does that work well? Yeah?
At the end, then you only be less than epsilon t.
Right. Well, so that is one of the two cases you argue that way. Right? So under what circumstances can you say I am within epsilon t of optimum? Yeah?
When the last job added to the busiest machine is small.
Right. So the point is that if, to analyze this greedy strategy, I can say if the last job to complete is small, then my runtime is less than or equal to opt plus epsilon times this t. In other words, 1 plus epsilon times opt. Right? So if the last job to complete after I do this greedy scheduling is small, then I'm fine. I'm close to opt. Okay, what's the other possibility? Well, yes?
You're at opt.
Well, if I could schedule all the large jobs optimally, I would be at opt. I'm not going to guarantee that. But what can I say if the last job to complete is large? Well, I can say that the small jobs don't matter. Right? So if the last job to complete, then the small jobs are irrelevant. So whatever approximation I'm able to achieve with the large jobs will be the approximation that I achieve for the entire problem. Okay, so the only question we have left to answer is, how do I get a good approximation when I'm scheduling just the large jobs? So we can now entirely forget about the small jobs. They don't even need to be considered as part of the input to the problem anymore. I've got an input where all of the jobs are large, and I want to schedule that close to optimally. Okay. Yeah?
You iterate with the large value of epsilon?
Can I iterate with a larger value of epsilon?
The very large job.
Oh, I see what you're saying. Interesting. I think what's going to get me in that case is that that larger value of epsilon is then going to show up in my approximation ratio, right? And I'm aiming for the smaller value of epsilon that I started with. It's a cute idea, though. Okay. So here's where I'm going to reduce to this small number of job types case. What I'm going to do is, for the large jobs, I'm going to round their sizes up to the next larger integer power of 1 plus epsilon. Okay, so we're doing this sort of geometric rounding, which we saw that before, right? The sort of geometric rounding approach. Why is this a good kind of rounding for the sort of problem that we're trying to, or for the class of problems that we're working with? Well, this only increases each pj to something that is less than 1 plus epsilon times pj, right? This is the really nice thing about this kind of powers, rounding to powers, as opposed to rounding to integers, right? Is that we're looking for a multiplicative approximation factor, and so we're willing to multiply everything by a little bit. Okay. Now, why is it good to round everything in this way? Well, now the number of job sizes, what are the possible job sizes after I do this sort of rounding? Yeah?
Will you have log t base 1 plus epsilon?
It's even better than log t, right? Because the problem is that t could be a huge number, right? So if I had log of t different values, that could be
Max pj. Correct. Log of max pj.
But again, that could be a big number, right? The pj's are arbitrary numbers. So I need something that's sort of independent of the numbers in order, if I'm going to argue that I have a good running time for all input instances. What are the possible sizes? Let's suppose that epsilon t is in fact a power of 1 plus epsilon, right? What other sizes do I get? Well, I get 1 plus epsilon t, or 1 plus epsilon times epsilon t, right? I get 1 plus epsilon squared times epsilon t, right? How far do I keep going in terms of sizes that I may have to consider in this problem? What's the biggest size that's going to matter? Can I have arbitrarily large jobs? Head shakes. What's the largest possible size of a job? T, right? If I have any jobs bigger than t, then I've got the wrong t, right? So how many different values are in here? Now you notice t is in every one of these, right? I can ignore t. I can just ask, what am I multiplying t by? So I'm multiplying t by epsilon, by 1 plus epsilon times epsilon, by 1 plus epsilon squared times epsilon. When do I stop? Well, I stop when this quantity becomes 1, right? If 1 plus epsilon to the k, or yeah, 1 plus epsilon to the k times epsilon being greater than or 1 means that I'm done, right? So for how many values of k do I need to think about, right? What value of k is this going to be? That's going to be at k equals log base 1 plus epsilon of 1 over epsilon, right? And that's a weird number, but it's a constant, right? You give me epsilon, I give you k, right? This is, if you do want to simplify this, this is roughly 1 over epsilon log 1 over epsilon. Okay? So I can read off a k that depends only on epsilon. And that's the number of job sizes that I will have when I round everything in this way, right? Oh my God. Okay. This is full of stuff I don't understand. Let's get rid of all that. So we have rounded to k equals 1 over epsilon log 1 over epsilon job sizes. So now we can use the enumeration solution. Which has a running time of n to the order k. Right? So we're done, right? K is a function of epsilon. So this is about n to the order 1 over epsilon log 1 over epsilon. Okay. And the only thing that I gave up is that I increased these job sizes, right? So this only made the optimum solution worse, but it only made it worse by a factor of 1 plus epsilon, right? So I find a solution that is optimal for the rounded jobs. And that means that it is less than or equal to 1 plus epsilon times optimal for the original jobs. And that's the end, right? I find a solution that is within 1 plus epsilon optimal of the large jobs. Then I throw in the small jobs. Either they matter or they don't. If they don't matter, well, then I just said I'm within 1 plus epsilon of optimal. If they do matter, then our argument about small jobs says that we're within 1 plus epsilon of optimal. So either way, we're within 1 plus epsilon of optimal. Okay? And our running time is polynomial, right? For any fixed epsilon, there is a polynomial. It's not a very nice polynomial, but this is why we have here a polynomial approximation scheme and not a fully polynomial approximation scheme, right? So this does give you something. Right? You could, as long as you don't make epsilon too small, you may have something that you can solve tractably. But also from a complexity theoretic perspective, it's nice to know that you can get as close as you want to the optimum solution. Okay? So this technique that I've just shown you is, again, sort of this sort of rounding and enumeration, brute force enumeration of all possible solutions involving the kind of big parts of the problem is, again, quite general. And in fact, it's general in the same sense as the sort of pseudo-polynomial algorithms were when we were looking at fully polynomial approximation schemes. So if anybody's interested, I can point you at a paper that basically says that if you have a problem that has a polynomial approximation scheme, then in an abstract sense, it's being solved using this kind of brute force enumeration. Okay, so last time I showed you this connection between pseudo-polynomial algorithms and fully polynomial approximation schemes and sort of connected that to weak NP hardness. Right? There's a similar connection here where any problem that has this sort of, if there's sort of this equivalence between these enumeration-based solutions for restricted instances and the polynomial approximation schemes for general instances. Okay? Again, it has to be phrased in a very abstract language in order to capture all possible problems, but that equivalence has been given. Okay, so now I've shown you some polynomial approximation schemes and even some fully polynomial approximation schemes. It's natural to ask, is there always one? Can we always make better and better approximation algorithms for every imaginable NP-hard problem? This would actually be really nice, right? It would keep algorithmists in business indefinitely. We could keep on cranking out better and better approximation algorithms. Unfortunately, the answer is no. So for decades, actually, people were not able to answer this question, right? Because how do you argue that you cannot approximate something, right? This actually required the development of a whole new branch of theoretical computer science to sort of explain what's going on here. And so a couple decades ago, people defined this class called max SNP. which are problems that can be approximated to within some constant, but not any constant. Okay, so you can approximate these problems to within some c, but not all constants. So there's some lower bound on the approximation factor that you can achieve. And they proved that there are actually, sorry, let me be careful about what I'm saying here. There are max SNP. So I think max SNP just means that you can approximate it to within some constant. But they proved that there are these max SNP hard problems, which cannot beat some constant. And just like in standard NP completeness analysis, they developed this whole theory of so-called approximation preserving reductions. Which show that if you can approximate this problem to within some factor, then you can approximate this other problem to within some factor. And using those reductions, they were able to show the equivalence of this large class of max SNP complete problems and argue that for all of those problems, right, if any of them has a polynomial approximation scheme, then all of them have a polynomial approximation scheme, and that P equals NP. Okay? So they were able to hang hardness of approximation off of our sort of fundamental notion of hardness of computation. Okay, and so we have strong evidence that you cannot approximate certain problems to within, there's some constant that you can approximate them to, but not better. Yes?
When you have a constant, you mean like a relative approximation, right?
That's right. This is all about relative approximation. Right? We abandoned additive approximation because it is so rare. And so this is talking all about relative approximations and being within some multiplicative factor bigger than 1. Yes?
Can you then generalize to an even worse approximation, like some sort of logarithmic approximation?
Yes. So the 90s were kind of the revolution decade for thinking about hardness of approximation. And there are many beautiful results. Probably the most important and prize-winning result was with regards to approximating and maximal independence set. They were able to show by developing what's called probabilistically checkable proofs, and this whole line of complexity theory that now has its whole courses about it and such. PCP can be used to show that clique cannot be approximated even to within an n to the 1 minus epsilon factor of the optimum. Okay? So even if there is a clique of size n, you can't find a clique of size n to the epsilon. So it's extremely hard to approximate. Yes? Probabilistically checkable proofs. Sorry, it's not what you think, right? Yeah, no, you know, sometimes on the weekend I like to take a few things and drift off into this land where all problems are tractable and, right? All right, so now there's this whole hierarchy of, there's this whole classification of problems according to how difficult they are to approximate. So there are some problems which have polynomial approximation schemes or fully polynomial approximation schemes. There are other problems which can be approximated to within some constant factor, but not to an arbitrarily good constant factor. Max SNP includes problems like vertex cover, which we've talked about. Certain kinds of the traveling salesman problem fall into max SNP. Then there are problems which are ordered log n hard. You can approximate them to within a log n factor, but not better. That's set cover is a canonical example of that one. Maximum satisfiability is another one. So they've really done they've really been quite comprehensively classified now that there are all of these problems that are known. There is some lower bound on the approximability. And in many cases, we're quite close to that in our upper bounds. In other places, we still have a large gap. Max cut is up here. Okay. All right. So how do you prove some of this? So in terms of how you prove some of these things, it's kind of like NP hardness. You needed somebody really smart to come along and give the first NP hard problem. And then it was just all reductions. So after that, right, you didn't need to be as smart anymore. You just needed to reduce to somebody else's smartness. And it's the same here. That sort of the hardness of clique is sort of the anchor point for a lot of this work on hardness of approximation. And you show other things hard by reducing to or from the hardness of clique. Okay. And you also use, another thing you can do is this sort of amplification technique. So we did some amplifications involving hardness of absolute approximations, right? We showed that if you could approximate absolutely to within such and such value, then you could get an exact solution, right? Or you could approximate to within a better value by scaling things. It turns out there are similar games that you can play with multiplicative approximations, with relative approximations. And so the optional problem on this week's problem set is an example of that. It gives you a little taste with regards to max clique. It shows that if you can approximate clique to within any constant factor, then you can approximate it to within every constant factor. So if there's a constant factor approximation, then there's a polynomial approximation scheme. So in order to prove that you cannot approximate clique to within any constant factor, all you have to show is some constant factor to which it cannot be approximated. And that's what the PCP theorem first did. Okay. All right, so a little bit of complexity theory culture. You should all go off and take 6840 and, or 6841 and the other complexity classes to learn more about that. Okay. So any questions before we move on to the next general and powerful approximation technique? No? OK, so the next thing we're going to look at, again, is a very general concept called relaxation. And I always find this very difficult to teach at MIT, right? But we'll do our best. It is Friday after all, so there's some hope that we can get there. So, right, we've seen these two processes. We've seen greedy and dynamic programming techniques so far. This is another approach, and a very general one. And the idea is, if you have a problem that you can't solve, then what you should do is come up with a different problem that you can solve. Okay, then you can solve it, right? So everybody's happy, except for the people who wanted you to solve the original problem, right? So the trick is to make sure that the problem that you can solve bears some relationship to the problem that you couldn't solve, and that the solutions to the relaxed problem are somehow relatable to solutions to the original problem. Okay, this will become much clearer when if we work through an example. And so the first example we're going to look at is the famous traveling salesman problem, okay, which everybody thought was solved by the interior point algorithm back in 1985, or sorry, the journalists, but in fact remains open. So I presume you've all heard of this TSP, right? You've got a set of vertices, you've got a set of edges. You want a tour that visits every vertex of the graph and comes back to its starting point of minimum total cost. Okay, and I mean, this is always told. They always tell the story of the salesman who's trying to visit all of his customers. I don't know if any salesman actually solved this problem, but it is actually solved a lot for delivery vehicles, for VLSI routing. There are a lot of applications of TSP, and there are people who've actually made their careers out of just solving TSPs. That's all of their research is how do we build better and better TSP solvers. So it's a real problem. So TSP is sort of interesting. If you consider general graphs and you actually require a tour, then there's no approximation at all because you can't even decide if there is a tour. Okay, because just deciding if there is a way to visit every city once and come back to the beginning is NP-complete. That's the Hamiltonian path problem. But if you loosen up the description and just say you have to visit every city at least once, right, then obviously you can do it, right? And in a sense, you've transformed into the sort of metric version of the problem. where we could assume a complete graph with triangle inequality on the distances. Okay, because as long as you're allowed to visit every vertex more than once, if you decide you want to go from x to y, you don't have to go directly. Instead, you can travel the shortest path in the graph from x to y. And so you can replace the edge from x to y with the length of the shortest path from x to y. And as soon as you've done that, you've created edge lengths that satisfy the triangle inequalities. Okay? So we're going to look at this metric TSP. Okay? And in fact, we are going to also look at the symmetric metric TSP. Okay? In other words, we're going to assume it's an undirected graph. So same edge length in both directions. We're not solving this problem in Boston, right, with all of its one-way streets and such. But you can go either way along any edge. Okay? Now, we can even start by considering a very restricted version of the problem called 1-2 TSP, where all the lengths of edges are 1 or 2, which means they obviously satisfy the triangle inequality, right? Okay, so you just have good edges and bad edges. Now, even this problem is max SNP hard. Okay? So there's some constant within which you cannot approximate it. Is there a constant within which you can approximate it? 2, right? Take any path, any tour, right? That's going to be at most twice the cost of the optimum. All right? But even this restricted problem cannot be solved to within there's no polynomial approximation scheme for it. There's some lower bound on its approximability. Okay? But we are still going to be able to come up with a constant factor approximation for the general symmetric metric traveling salesman problem. Okay? And this is based on the idea of a relaxation. So what we're going to do is we're going to take this problem which says find a tour which visits every vertex once and comes back to its starting point. And we are going to develop a problem which is kind of like it. In particular, every solution to the traveling salesman problem is also going to be a solution to our new problem. Okay? So we're going to create this relaxation where every solution to the original TSP is a solution to our problem, to the relaxation. That's kind of the definition of the relaxation. We're removing constraints. We're allowing everything that was feasible before to still be feasible. And the important thing about that is that it guarantees that the relaxed optimum is as good or no worse than the original optimum, right? Because we're allowed to use the original optimum. But the other critical feature of the relaxed problem is that it should be tractable. So we can solve it. So we can find a solution to the relaxed problem, which will be at least as good as the solution to the original problem. But immediately answer the original problem, because the solution that we found may not be a valid solution to the original problem. We've relaxed the constraints. There are more possible solutions. So our final step is that we are going to round our solution to something feasible for the original problem. Okay? And that's not just going to be a numeric rounding. It's going to be a sort of a structural change that brings us back into feasibility to the original problem. But it is a kind of rounding in the sense that that's going to cost us something in the value of the solution. The solution is going to get worse as a result of the rounding process. But we're going to bound the amount by which it makes the solution worse, and that's going to let us claim that we have a good approximation. So general strategy clear? So let's come up with a good relaxation. So the traveling salesman problem wants to connect up all of the vertices in a tour. Tours are complicated, or intractable. So Let's throw away that part. Let's just say that we want to connect up all the vertices. We still want to minimize the cost. Can I solve that problem? Can I say, if I want to just connect up all of the vertices at minimum cost, and I don't care if it's a tour or not, is that a tractable problem? Yeah? That's minimum spanning tree, right? So the relaxation of TSP is going to be to connect all the vertices at minimum cost. Okay. And of course, we can solve that using MST. All right. But you'll notice that OK, so now we have to be a little bit careful because the tour has sort of an extra edge in it that is not, it's not a tree, right? It's a cycle. But even if we take out that edge, right, what we have left is a tree. It's a very skinny tree, right? But it's a tree. So we can just look at that, and that tells us right away that the cost of the minimum spanning tree is less than the cost of the traveling salesman problem, less than or equal, right? So we're well on the way to finding a solution to the traveling salesman problem, except we don't have a tour. We have a tree. So now what we need is a way to round the MST to a tour. Okay, so I've got this tree, and I know it's cheap. It's a cheap tree, not one of those exotic Amazonian rainforest trees, but something cheap, right? And from that, I need to get a tour. So let's ignore the rest of the graph, right? I've got this cheap tree. Can I use this cheap tree to tour around the vertices? Yes?
If you imagine the edges as like hallways, then you can do wall following?
Yes. And on a tree, this is just depth first search, right? So I can certainly explore a tree by depth first search. Right? So what can I say about the cost? If I'm going to use a depth first search to navigate this tree, how does the cost of that depth first search compare to the cost of my tree? Yes?
Well, you're going over each edge at most 2 times.
Exactly. So this traverses each edge twice. It's actually exactly twice. Right? I go down and then up. Right? And that means that the cost of my tour is equal to twice the cost of my MST, which therefore is less than twice the cost of the traveling salesman problem. And therefore, once again, we have found a ultimate solution to an NP-hard problem, right? And so, it's really a good thing that we took this break with polynomial approximation schemes, because you might think that all problems were proximal to within 2, right? But I think it's actually natural. It's kind of reasonable for problems to have integer approximation ratios. And if they're going to be integers, then 2 is the best one you can hope for. So why not, right? So everybody happy with this approximation? Yes?
Not a tour yet, but we didn't.
Oh, no. So if we do a depth first search.
No, I mean, isn't the path, the MST path, like not necessarily a.
Well, that's why we're exploring by DFS. In other words, so if this is my tree, right, the tour goes like this. Oh, I see what you're saying. I'm visiting vertices more than once. Good. So what do I do about the fact that I'm visiting vertices more than once? If I actually want to make a tour, what should I do? Just take shortcuts, right? So I can shortcut duplicate vertices. Right? If my tour is taking me back to a vertex that I've been to before, and then onto another vertex, there's no need for me to visit the vertex I've already been to. I'll just skip it and go straight to the next vertex that I haven't seen in the tour, right? Now, this, because of our metric assumption, this does not add anything to the cost. right? Because shortcutting out a vertex never adds cost if you have the triangle inequality. Okay? Good, so good point. So yes, but this will make it a tour, right? So we're done. Okay. Now, this turns out not to be the best that we know how to do for traveling salesman problem. Christofides in 73 realized that we can do better than a factor of 2. And it started from the same concept, that the minimum spanning tree is a good relaxation of TSP. Right? It shares a lot of the characteristics. It's cheaper. What he did was come up with a better rounding idea. And the sort of the intermediate point that he thought about for rounding, sort of, we tried to go straight from a tree to a tour, right? One giant cycle. His idea was that to go only part way, to go from the tree to a so-called Eulerian graph. So an Eulerian graph is a graph where every vertex has even degree. Okay? And one of the nice things about Eulerian graphs is that Eulerian graphs have Euler tours. So again, I'm assuming many of you have seen the whole, bridges of Göttingen puzzle, right? Can I walk around this city traversing every bridge exactly once that Euler worked on? So an Euler tour is a traversal of the graph that crosses every edge exactly once. Okay? And this is appealing, right? If we could take that minimum spanning tree and traverse every edge only once, then we wouldn't cost twice as much as the TSP. We'd cost less than the TSP. Right? Why can't we traverse every edge of the minimum spanning tree only once? Yeah?
You have to cross an edge to a leaf twice.
Yeah, the problem is, or an obvious problem is with the leaves, right? If I traverse an edge to get to a leaf, then I have to traverse I have to go back on the same edge in order to get away, in order to leave the leaf, right? And so this is the problem. I would call it the root of the problem, but it's actually the leaf of the problem. So it is, right? That these vertices here have degree only 1. Right? So there's no way that if the degree is 1 that you can traverse the edge, that you can traverse each edge only once. And more generally, if you think about it, if a vertex has odd degree, then I can enter on one edge and leave on another, but that's going to take away 2 edges that I can't use anymore. So if I keep taking away pairs of edges like that, and I end up with an odd degree vertex, then I get stuck again. So you can prove that what allows you to traverse an Euler tour, to traverse every edge exactly once, is if every degree is even and the graph is connected. Okay, so if you can create a connected graph with even degree, then you can traverse every edge exactly once. So that's what Christofides set out to do. He set out to take this minimum spanning tree and turn it into an Eulerian graph. Okay, so his idea was to add edges to make the minimum spanning tree Eulerian. Once it's Eulerian, you traverse all the edges exactly once, and that gives you your tour. So what's the cost of this tour? It's the cost of the minimum spanning tree plus the cost of whatever edges you added in order to make the graph Eulerian. Okay. Right? We know that the MST is less than the TSP, so really we just need to bound the cost of the edges that we need to add in order to make the graph Eulerian. Okay? Now, given what I've said about, odd vertices being the problem for a graph, where do I need to add edges in order to make the graph Eulerian? Yeah?
You need to have exactly one edge for every pair of odd degree edges.
Exactly. I need to take all the odd degree vertices, or sorry, one way I can make the graph Eulerian is to take all of the odd degree vertices and pair them up and draw the edge between them. Right? So let me just write that down. One way is to pair the odd degree vertices and connect each pair by an edge. And remember, we're assuming we have this complete graph with triangle inequality, so that edge exists to do the connection. Yes? Question?
Can you have an odd number of vertices with odd degree?
Good question. Can you have an odd number of vertices with odd degree? How come? Yeah?
You're counting each edge twice for every vertex that it belongs to, so an odd degree plus the even number would result in an odd number.
Exactly. If you sum the degrees, what you're doing is counting every edge twice, once for each endpoint. And so that's an even number. So the sum of the degrees is even. Therefore, you have an even number of odd degree vertices. So it is possible to find these pairings. In fact, you can put this in the language that we've worked with before. This is just a matching, a perfect matching on the odd degree vertices. Right? Now, we studied bipartite matching in a bipartite graph, but there's a very natural generalization to non-bipartite graphs. Right? A perfect matching is where you take all the vertices and you pair them up with edges connecting them. And so there's the natural questions to ask. Does such and such graph have a perfect matching? Right? You can ask that. Here, we know there's a perfect matching because every pair of vertices is connected. Right? But we can ask for a min-cost perfect matching. That seems like a pretty natural thing to hunt for if we want to minimize the cost of our Euler tour. Right? And so I will assert to you, we haven't proven it, we haven't shown it, but you can solve min-cost perfect matching in polynomial time. Okay? This one, unfortunately, does not use flows. You have to get more sophisticated. It sort of is based on some ideas from matroids. But you can do it. And that's been known for a long time. So I can find this min-cost perfect matching, which seems like the best way to transform my MST into an Eulerian graph. The question is, how good is that min-cost perfect matching? Can I compare it to the cost of the tour? Okay. So we need to compare this to the TSP. And what we want to show is that there is a min-cost perfect matching that's cheap compared to the TSP. Okay. How can we do that? Well, the obvious place to start is by looking at the TSP optimum. Right? So here's my TSP tour. Okay. Now, for starters, this tour is going to this is the optimum tour. It involves all of the vertices of the graph. But for starters, I'm going to shortcut out all of the even vertices so that I'm left only with the odd degree vertices. So I can create a tour through the odd degree vertices. And since I've only been shortcutting, this only reduces the cost of the tour. Right? So we're going to shortcut the even vertices. Okay. Which is going to decrease the cost. And now I have a tour on the odd vertices. So now that I've got this tour on the odd vertices, can I say something about perfect matchings between the odd vertices? Actually, these we just said I have to have an even number of odd vertices, so let me do that. Okay. So can we say anything about perfect matchings among these odd vertices?
Yeah? It's less than or equal to half of the case.
How come?
Well, if you just take alternate, then
Great.
one of the two sums has to be less than or equal to.
So let me just label these edges alternately A and B. Okay. The A edges form a perfect matching, right? The B edges also form a perfect matching, right? So in fact, this is equal to two perfect matchings. So if I can make the tour out of two perfect matchings, one of those two perfect matchings must be half of the tour. So instead of running all the way across to the other board, let me just finish the story here. Right. So perfect matching is less than or equal to 1/2 of the TSP. Yes? Sorry, question?
Well, how do we know that we're not using edges from the minimum spanning tree?
It's actually fine if we do. So suppose that my batching includes an edge from the minimum spanning tree. The way to think about that is that I've just put another edge here. So now I have two parallel edges. The degree, and each can be traversed once. Does that make sense? Okay. So I find this perfect matching. Its cost is less than half of the TSP. So my solution costs less than the minimum spanning tree plus the perfect matching, which is equal to 3/2 of opt. So finally, an approximation ratio that isn't 2. Right? You can approximate TSP to within a factor of 3/2. Any questions about that? Can we do better? That's always the right question for an algorithmicist to ask, right? And the answer is yes, although it took a long time. So for a long time, nobody had any idea how to do better. Then some people, Held-Karp, developed something called the Held-Karp bound. And the Held-Karp bound was sort of an idea for doing a different, for changing the relaxation of the traveling salesman problem to make it tighter, right? So the notice of, we haven't really talked about it yet, but having a tight relaxation means having a relaxation that's a lot like the original problem. And if it's a lot like the original problem, you can hope that the solutions to the relaxation are closer to solutions to the original problem, so you lose less when you round them. So the Held-Karp bound can be seen as a way of kind of reweighting. It's kind of like adding a price function to the minimum spanning tree. So the problem with the minimum spanning tree, if you think about it, is that there are vertices that have the wrong degree. Right? If your minimum spanning tree has degree 2 everywhere, then you're very happy. Right? The problem is that there are vertices of degree 1 and there are vertices of high degree. So what do? Well, you add a price function to the vertices, which makes degree 1 vertices cheaper and high degree vertices more expensive, and sort of therefore drives minimum spanning tree edges away from the high degree vertices towards the low degree vertices to try to balance out the degrees. Okay? And this can be formalized also in terms of an interesting linear program. And they worked and worked and worked, and nobody was ever able to find an example of Held-Karp which was off by more than 4/3. Right? So if you're going to go past 3/2, then 4/3 is the obvious thing to go for next, right? So nobody was ever able to give an example of something of a worse than 4/3 approximation ratio between the Held-Karp bound and the optimum of the TSP. Okay? I believe that's still true. I believe that nobody has come up with a contradiction. And so one interesting open problem is to try and prove that the Held-Karp bound is within 4/3 of the optimum. That's not what people have succeeded in doing. However, just a couple of years ago, and I forgot to write down the names of the authors, they did manage to come up with a 3/2 minus epsilon bound for TSP. Just a couple of years ago, right? So this is still completely open, and there's still progress to be made right now. Yeah?
So all this that we did so far was for metric TSP.
That's correct.
But this one is...
No, the 3/2 minus epsilon is also for metric TSP. If the TSP isn't metric, then again, we have this problem that it includes Hamiltonian paths, so there's no way you can approximate it at all. Okay, right? If you're not metric, you could have a TSP problem with ones and infinities, and then it's not clear that you can find a solution, that you can find a tour at all. But so they were able to give 3/2 minus epsilon, and it's people here, I think, at MIT. Yes?
I think it was Asatpur, Madri, Gomez, Police.
Right. So I know Madri. Did anybody go to his talk today?
It's today.
Sorry, it's today at 4 o'clock, right? So I'll advertise that later. So Madri, Gomez, what was it? Asaf or?
Asatpur.
So what?
P-O-U-R. Asad. A-S-S-A-D. P-O-U-R.
Asapur, Madri, Gomez, et al.
Yeah.
Right? So that was, I mean, it was an amazing breakthrough because 3/2 has been sitting there since 1973. Right? But this is just saying there are more breakthroughs to be made. Right? But it's a very small epsilon. Right? So we're a long ways off from the 4/3. On the other hand, we know that it's max simply hard. So, I mean, for a while, people thought, well, maybe you can't be 3/2. Maybe that is the lower bound for approximation. But now we cannot, right? That can't be the lower bound anymore. And you've got to assume that the actual bound, the best possible constant, is some sort of nice number, right? It's not going to be some random irrational number, right? So you know, 4/3 seems like a good thing to aim for as the next possibility, and the Held-Karp bound seems to be plausible for going there. I'll also mention that there's the directed TSP, right? The Boston version of this problem, where you have one-way streets. Okay, that problem is a lot harder. But it also has an interesting approximation algorithm. It turns out that you can achieve order log n using a relaxation to something called cycle cover, which says, I'm not going to try and find one tour that covers all the vertices. Instead, I'm going to find a whole bunch of small tours that covers all of the vertices. And doing that, using that as a relaxation, it's possible to get a log n approximation for directed TSP, and I'll probably put that on your homework next week. So you get a chance to play with that. Okay. Here too, there's been recent progress. I think again by Gomez to order log n over log n. But I think Michelle thinks that a constant should be possible, and there's no reason to believe that it's not. There's no hardness result. So this is still a very active area, you know. So for the basic problems like, well, I can't say that flow is no longer an active area because come at 4 o'clock. There's this wonderful talk about interior point methods for max flow and how you can get better bounds. But approximation algorithms is still a tremendously open area. There's lots of problems, lots of gaps between the upper and lower bounds, lots of progress to be made. All right. Let's take a break now, 2 minutes, and then I'll show you another relaxation or two. So the next problem I want to look at is some Cj. So we have a bunch of jobs, and we have one machine on which to complete the jobs. Now, when you have one machine, Cmax is not a very interesting objective function, right? Sorry, if you don't have any other constraints on the problem. But some Cj, in other words, the average completion time, is still an interesting thing to try to solve, right? So, and I mean, you could think of this as, you know, it could be a machine or it could be a person, right? A person has a whole bunch of jobs to do. Which jobs should they do first in order to kind of get things done on average as quickly as possible, right? So any thoughts about, say, a plausible greedy strategy for this problem? Yes?
Do the smallest.
Smallest jobs first. So this is called shortest processing time first. It's written SPT. Okay, why is this intuitively a good idea? Well, if you think about it, if you do the small jobs first, you're kind of finishing as many jobs as possible soon, right? So this is going to pull down the average completion time. So how good of an approximation do you think that this achieves? 2. Good guess. Any other ideas? What could get in the way of this being a good good solution? Nothing. This is actually an exact solution. Gotcha, right? Okay. So, why is this an exact solution? Right? Why is this optimal? How do we prove it? Yeah.
Suppose that two jobs were ordered in the wrong way. If you switch them, the only thing that changes is one.
So the proof of this is something that's used a lot in scheduling theory called an exchange argument. If the jobs are not being done shortest first, then there's two of them that are in the wrong order and adjacent to each other. Right? You just keep going up until you see something go the wrong direction. There has to be a flaw in the order. So you look at that place, you say, what happens when I switch the jobs? So it's a pair of jobs. Switching them doesn't change the completion of the second job of the pair. Right? Whichever one is going last is still finishing at the same time. But if you move the shorter one first, then the first of the two finishes sooner. Right? So if Pj less than or is greater than Pj plus 1, then you're contributing two terms to the completion time, one at this spot and one at this point. Then the swap leaves J finishing at the old J plus 1 completion. But J plus 1 finishes sooner than J did. So we've lowered the average completion time, lowered the sum of completion times. Yes?
This is a really bad question. Why is sum of CJ the average?
Because in order to get the average, I just need to put a 1 over n here, which is just a scalar multiplying the average. And so it just means I can save on ink and chalk by writing this objective function instead. Okay? And I mean, this is all about optimization, so saving chalk is good, right?
Can you repeat the problem statement?
Yes. So the problem statement here is that I have one machine, a set of n jobs with different processing times, Pj, and I want to minimize the sum of completion times, which is also the average completion time of all the jobs. So I need to figure out an order on which they're going to run on this one machine, and I add up when all of them finish, when they run in that order. Because I'm looking at the sum of completion times and not the maximum completion time. Right? So I'm going to line up the jobs on the schedule. Right? And so this completes at time 1, this completes at time 4, and this completes at time 9. Right? So I add them. And so the sum of completion time is determined. If I swap the jobs, it changes the sum of the completions. Obviously, the C max is 9, but that's OK. It's the sum of completion times that I care about here. Okay. All right, so what I've proven here is that, right, if you are globally optimal, then you are locally optimal, right? And so you sort of turn that around and say the only way to be locally optimal everywhere is to be in increasing order. So we're done. Yes?
Is this the rearrangement inequality?
Is this what?
The rearrangement inequality?
I'm not sure. I've never heard of the rearrangement inequality. I mean, I've always heard it called the exchange argument. So I think that's a pretty standard name for it. Okay. Good. So why did I show you this problem? Well, because the machinery is useful for the problem that we actually want to talk about, which is one Rj sum Cj. So now each job comes with a release date. And you cannot execute the job before the release date. This makes the problem somewhat harder, namely NP complete. Well, it might not be harder. We don't know for sure, but at least for us, it's harder. So what makes it hard? I mean, why is this problem suddenly so much harder? Yeah?
Are we assuming that we cannot preempt a task?
I'm not, so in this statement of the problem, there is no preemption, right? So you start a job, you still have to specify this is the order in which I'm going to do the jobs, right? But preemption is a very interesting idea that we'll come back to. So why is this difficult? Yes? Exactly. All of a sudden, because of these release dates, it might make sense for you to not work on an available job, right? You might decide, well, there's this big job I could work on now, but if I wait a little while, then this whole bunch of small jobs is going to show up, and I can take care. If I'm working on the big job, then I can't do the small jobs. So better for me to defer the big job and work on the small jobs instead, right? So now I have actual complicated decisions to make, which is why this problem becomes so much more difficult. Okay. However, we can do pretty well on it, and the approach we're going to take is a relaxation approach. So we're going to try to reduce the constraints of the problem in a way that makes the problem tractable, and then round the solution to the tractable problem back into a solution to the original problem. Okay. And the relaxation that we're going to use is exactly what was just proposed, this idea of preemption. So we're going to relax this problem to one RJ preemption. Whoops, sorry. Some CJ. Okay, so preemption is when you stop running one job and switch to running another one. And then when you come back to the first job, you get to pick up where you left off. So this is very problem dependent whether this is a reasonable or an unreasonable assumption, right? With a lot of computer processing, preemption is very reasonable. You swap it out, you bring it back later, right? If what you're doing is assembling a watch and you've got all of these gears halfway in, then it's probably a bad idea to preempt that task in the middle and lose all of the pieces, right? But it is a relaxation, right? Because obviously any non-preemptive schedule is also a preemptive schedule. So any solution to this is also a solution to this. But we've only changed the problem somewhat, and so hopefully a solution to this can come back to help us solve the original problem. Yes?
Clarification. In the original job, are you allowed to not work on anything?
Yes, you are allowed to not work on anything. Okay. So how might we solve the problem if we are allowed to preempt? Yeah?
Do shortest job, and then at the release time, you reevaluate the shortest job is.
Good. So there's a heuristic called SRPT, where the R stands for remaining. So at any moment in time, you should be working on the job that has the least work left and is available. So some jobs haven't been released yet. You can't do those. But of all of the jobs that have been released up to this point, you work on the one with the least work yet to be done. And whenever a new job is released, you have a new decision point where you say, is the new release job shorter than the one that I'm currently working on? If so, I will swap. Now, why is this a good heuristic? Right? This turns out to be optimal for the preemptive case. What would the intuition or formalism be for arguing that this is optimal? Yeah?
If you work on a job that isn't the shortest remaining one, then might as well just work on the shortest remaining one.
Good. So that's the intuition, and we have the technique available for formalizing it just as we did for this case, which is why I showed you this case, right? So we can use the exchange argument not on whole jobs, but on pieces of a job, right? So the proof is an exchange argument again. Where if I'm not working on the shortest job, I can improve my sum Cj by swapping. And this is just a little messier. It's not any harder to prove, but it's messier because now you've got all of these different pieces of jobs floating around, right? But what I can do is I can fix my attention on any two jobs, right? So here's a time when I'm working on not the shortest remaining processing time. So let's also find the job that has the shortest remaining processing time and just look at the current job and the shortest job. If I don't move anything else around, none of the other completion times change. So if I can argue that there's a way to swap things that change things just for these two jobs, then I will have derived my contradiction, right? So consider the current job and the shortest remaining job. Okay, so I don't know anything about, and let's call these Pj and Pk, or Pk for the current and Pj for the shortest remaining. So I don't know anything about the other jobs, but I can look at the moments in time when I'm, right now I'm currently working on Pk, and sometime later on I'll work on Pj for a while, and then maybe I'll work on Pk some more, and then maybe I'll work on Pj for a while, and then Pk. So what sort of exchange argument do I make? Well, it's really silly for me to be kind of mingling work on these two jobs, right? Because that just makes both of them later, right? Obviously, if I just consider these two jobs, I should push all the work on one of them first and then do all the work on the other one, because that moves the first completion, right? So however I rearrange the work, it's not going to change the completion time of the second to finish, but I can push back the completion time of the first to finish. What's the best way to push back the completion time of the first to finish? Is take the shorter of the two and do all of that in as much of these intervals as I need. Okay? So that proves that SRPT is optimal for the preemptive case. Okay? So all we have left to do is take our preemptive optimum and round it to get a solution to the original problem. So here I've got this preemptive schedule, job starting, stopping, restarting, restopping. How can I turn that into a non-preemptive schedule? Well, what I'm going to do is run the jobs non-preemptively in order of their preemptive completion. So I'm going to use the preemptive schedule to tell me the order in which jobs should be done. Now, I'm not going to use the order in which they start. I'm going to use the order in which they finish. And that's going to be the order in which I won the jobs. This may require waiting. Right? If I look at my order, I do job 1 because it's available at the beginning. And when I finish, job 2 still isn't available. OK, I'll just wait until job 2 is released, and then I'll do job 2. Okay, I'll just run in the same order as in the preemptive schedule. Why is this a good idea? So what I now need to do is relate this schedule to the preemptive schedule. And the way that I'm going to do that is I'm going to sort of give a direct transformation of the preemptive schedule into the non-preemptive one. Sorry, I lost my place. So how long might I have to wait to start Pj? Right, so Pj finished at some certain point in the preemptive schedule. Now I'm running the jobs non-preemptively in the order in which they were they completed. How much might I have to wait for Pj? Well, I can think about this by sort of proactively adding sufficient waiting time for everything. So what I'm going to do is I'm going to consider adding sorry, how do I want to say this? Right. So if I start with the preemptive schedule, it has its little pieces. Right? And job J is going to finish at some point in the preemptive schedule. Now, when I switch to the non-preemptive schedule, okay, I'm going to have to introduce some waiting space that wasn't there before. Right? But how can I bound the amount of sort of extra waiting space that's going to have to be created because I am not preempting things? Yeah?
Is it like the completion time of PJ in the preemptive schedule minus the start time minus the length of PJ? It's like all the time you spend processing in the preemptive schedule between when you started and when you finished that wasn't on PJ.
That's right. It's basically the amount of time that PJ is going to have to wait is just dependent on the jobs that were put into this, that were being processed before PJ in the preemptive schedule. Okay? So I can think about this as I'm inserting enough space, PK, before J for every job that completes before J in the preemptive schedule. Okay. So that's sort of the total amount of idling that I'm going to have to do before I actually get to run job J. In other words, the total delay added by not preempting is at most the sum over k before J of pk. But what is this sum? What is the total processing time of all the jobs that run before J? Well, that clearly is at most the completion time of job J. Okay, because if all of these preemptive jobs are finishing before job J, then they're finishing before the completion time of job J. And this is in the preemptive schedule. Right? The completion time of job J is at least the sum of the processing times of everything that came before. Okay. Therefore, that's the delay added to job J is Cj. So that means that the completion time of J is at most twice the preemptive completion time. And therefore, our solution is at most twice the optimum preemptive solution and is therefore at most twice opt. So once again, we have a 2 approximation to the optimum. Okay. Now, this is not the best you can do. It turns out that there is a polynomial approximation scheme for this problem. Okay. And it involves the same tricks as we used before, rounding to integer powers of 1 plus epsilon, doing brute force enumeration on the large jobs, so on and so forth. It's a fun exercise to try and work it out. But now I've sort of shown you, I think, a couple of really nice relaxations where the relaxed problem has a very natural relationship to the starting problem. And so it is sort of unsurprising that you can transform a solution to the relaxed problem into a solution to the original problem. Okay? On Monday, I'll show you even more sort of general approach to relaxation, which relies on the fact that you can express many of these problems as integer linear programs. And once you have an integer linear program, there's a very natural relaxation to look at. So that'll be our Monday topic.